All right, if you've ever cracked open a physics book like Irodov and felt that little bit of panic, yeah, you're not alone. So today, we're going to tackle one of its most famous problems, 1.85. And trust me, by the time we're done, you'll see it's not as tough as it looks. Okay, so let's get into it. You look at this and it's like, okay, it's a pendulum. Big deal, right? But this problem is so clever because it's built to test a concept that trips up so many students in mechanics. And that's this idea that acceleration isn't just about speeding up, it's also about changing direction. Seriously, if you can get your head around this, you're going to unlock a ton of other circular motion problems. Whoa, okay, that is a wall of text. Let's just ignore that for a second and break it down. Here's what they're really asking. Part A, can we come up with a master formula for the acceleration and the tension that works no matter where the pendulum is in its swing? Part B, what's the tension when the ball is moving down the fastest? And part C, can we find the exact spot where the acceleration vector is pointed perfectly horizontal? That's it. We're just going to knock these out one at a time. Okay, so before we write a single X or Y, let's just take a breath and visualize this thing. What do we actually know, and what are we trying to find? Seriously, getting this picture straight in your head first makes all the math that comes later so much easier. So here's the setup. The ball starts way up high, totally horizontal. That's 90 degrees from the vertical, and it's just hanging out, not moving. Then we let it go, and as it swings down, our mission is to create these two powerhouse formulas, one for its acceleration and one for how tight that string is, the tension. And the cool part is, these formulas have to work for any angle theta along that path. All right, let's talk about our game plan. You know, what I love about this problem is that you don't need to memorize a million different equations. The whole thing, all of its tricky parts, really just comes down to two big ideas in physics. It's all about picking the right tool for the right part of the job. So here it is, our two-step plan. First up, conservation of energy. Why start there? Well, because energy is simple. It doesn't have a direction, it's what we call a scalar. That makes it the perfect, easiest way to figure out how fast the ball is going. Just the speed. Then, once we've got the speed locked down, we bring in the heavy hitter, Newton's second law, good old F equals ma. This is the tool we need for things that have direction, like forces and acceleration. Okay, let's do this. Time to get our hands dirty with part A. The goal here is to build those master formulas for acceleration and tension. Think of these as the keys that are going to unlock the rest of the problem for us. So, let's track the energy. First thing, let's just decide that the very bottom of the swing is our ground level, our 0 point for potential energy. Makes life easy. That means when it starts way up at the top, it has a ton of potential energy, right? And as it swings down, all that potential energy gets traded in for kinetic energy, the energy of movement. And how much height does it drop? Well, with a little trig, you can see it's r times cosine theta. So the potential energy it loses is exactly equal to the kinetic energy it gains. We write that down, shuffle the terms around a bit, and boom! We get this awesome, super useful formula for v squared. All right, speed, check, we got that. But now we hit the part where almost everyone makes a mistake. Acceleration. It is so tempting to just think about whether the ball is speeding up or slowing down. But I'm telling you, for anything moving in a circle, that's only half the picture. You have to think of the total acceleration as having two components, two little workers doing completely different jobs. You've got the tangential acceleration, that's the one pushing it along the arc, making it go faster and faster. Then you've got the normal acceleration. Its only job is to constantly pull the ball inward, to change its direction and keep it moving in that circle. You can't forget about him. You absolutely need both. So let's plug things in. The normal acceleration, that's the one that depends on speed, is just v squared over r. So we can pop our new v squared formula right in there. The tangential acceleration, that's just a little piece of gravity that's pulling it along its path. Now, since these two accelerations are always at a perfect 90-degree angle to each other, we can find the total acceleration just by using Pythagoras. Simple as that. And what about the tension in the string? Well, think about the forces pointing along the string. It's like a little tug of war. You've got tension pulling the ball in towards the center, and you've got a little piece of gravity trying to pull it out. The winner of that tug of war, the net force, is exactly what's causing that normal acceleration we just calculated. So we set them equal, F net equals ma normal, do a little bit of algebra, and what pops out is this really clean, simple formula for the tension. Okay, we did the hard work. We built our general formulas. Now for the fun part. Let's look at parts B and C. With these tools we've made, solving these specific little puzzles is going to be way, way easier. It's just a matter of plugging in the right numbers. Okay, part B. Now pay close attention to the wording here because this is a classic Irodov trick. It asks for the maximum vertical component of the velocity, not the total velocity. Those are two totally different things, and if you mix them up, you'll get the wrong answer. So we have to be super careful here. Okay, so how do we find the vertical part of the velocity? A little bit of trig tells us it's just the total velocity, v, times the cosine of the angle. Now we already have a formula for v, so let's substitute that in. Take a look at the equation we get. It's got some constants in there, like g and r, but the only thing that's actually changing is that cosine term. So if we want to make the whole thing as big as possible, what do? We make cosine as big as possible. And what's the biggest value cosine can ever be? It's 1. And when does that happen? When the angle theta is 0, right at the bottom of the swing. And with that, finding the tension is a piece of cake. We go back to our master formula for tension we derived earlier, and we just plug in theta equals 0. Cosine of 0 is just 1. So the tension is 3 mg. That's it. The tension at the very bottom is 3 times the weight of the ball. All right, on to the last piece of the puzzle, part C. And this one is a really great question. It's a real test of whether you understand how vectors work. So think about it. What does it actually mean for that total acceleration arrow to be pointing perfectly sideways, perfectly horizontal? Well, if the final result is purely horizontal, it has to mean that any upward motion and any downward motion have perfectly canceled each other out, right? They have to be in perfect balance. So let's look at our two acceleration components. The normal acceleration points partly up, the tangential acceleration points partly down. For the total to be horizontal, the vertical piece of the normal one has to be exactly equal to the vertical piece of the tangential one. So we set them equal, and that gives us the equation we need to solve. When you solve that little equation, you find the angle is about 54.7 degrees. Now, here's a cool little insider fact about this problem, a bit of an Easter egg. If you calculate the tension at this specific angle, you get mg times the square root of 3. And for some reason in a lot of the old answer keys for the Irodov book, that value is accidentally printed as the answer for part B. Just a weird little quirk of this famous problem. Okay, we did it. We solved the whole thing. But what's the point? What are the big lessons from this one problem that you can take with you to the next one? Let's boil it all down to the key things you need to remember. Okay, takeaway number 1, and if you remember nothing else, remember this. Never forget the normal acceleration. If an object is turning, it has it. Period. It's not optional. Takeaway 2, remember our 1-2 punch strategy. Energy first to get the speed because it's easy, then F equals ma to deal with the forces. And finally, like we saw with that whole vertical velocity thing, read the question. I mean, really read it. Every word matters. All right, so I'm going to leave you with a little challenge just to really cement this in your brain. Go all the way back to the beginning, to our energy step. But this time, what if we didn't start from 90 degrees? What if we started from some other random angle, let's just call it alpha? How would that one little change at the very beginning ripple through and change our final formula for tension? Seriously, sit down and try to work that out. If you can do that, you've absolutely mastered this concept. Thanks for sticking with me.